Welcome back, everyone, for the last session of PriSC. So this session is the secure system session, and the first talk is from Paolo Torrini, who is going to present a CompCert backend with symbolic encryption. Paolo, the stage is yours.
Hello, everyone. Thank you very much. I'm very pleased to present this work to you. I've been working on, together with Sylvain Boulmé, at Verimag. Most of the work was made about 2 years ago, but we've kept on working on it on and off. And basically, it's adding symbolic encryption to a RISC-V CompCert backend. And the motivation, of course, is preserving code integrity and control flow integrity. Attacks in general may exploit either hardware faults or buffer overflows. And there are attacks that target code integrity by reusing code in malicious way. There are attacks that target and can break control flow integrity by causing an overflow in the stack and diverting control flow by altering the return addresses that are stored on the stack. In general, a mitigating policy to protect from attacks is separate executable code and rewritable data. But we know that this is a big limitation. For example, the stack is data, so we need to go beyond. And this is essentially a quite applied work that we've done, in the sense that it's a sort of case study on what can be achieved in this direction, working on with an existing system like CompCert. But we basically took inspiration from Abadi's work on control flow integrity for the part about the security properties. So the project we worked on is Nanotrust, and the general approach is to protect integrity by using binary code encryption. So relying on a trusted compiler, which should be formally verified, and aiming at secure compilation. And we're interested in compiling C code, and we are targeting RISC-V 32 bits. The project was a collaboration between Verimag and the CEA, the French agency for atomic energy. And at CEA, they co-developed an LLVM compiler with multiple levels of encryption and a matching RISC-V processor. Whereas we at Verimag, we developed the certified compiler we are going to talk about in this presentation. We call it IntrinSec. As I say, it's based on CompCert, and it's a RISC-V backend extended with an abstract model of symbolic instruction level encryption. So first we say something about different ways in which encryption can be used and has been used in this project. First of all, program level encryption, which consists in encrypting the whole program, possibly by a strong heavyweight cryptographic key. We can also consider pointer level encryption, which is more direct to actually protecting data, relying on fat pointers. But this is something that we haven't formalized in Coke. Whereas we are going to focus specifically on instruction level encryption, which basically consists in encrypting each single instruction by a lightweight key, which is a 32-bit mask. And each function is associated with a finite stream of masks. We call this a stream cipher, synchronous stream cipher, which basically means that the first mask, the initial mask for each stream is generated from a seed, and then there is an XMask function that brings from one mask to the next one in a pseudo-random way, essentially. So this is the cryptographic machinery we are building on, and we are essentially implicitly formalizing in CoC. So this is the a simple diagram of instruction level encryption. There's nothing complicated. You can see just the function block and the cipher and the stream cipher, which are basically associated instruction-wise. And the processor has a program count pointing to an instruction, and an additional register, which is a mask counter, which should point to the mask, which is sequentially associated to the instruction that should be decrypted. So if the mask in the mask counter is the right one, the decryption can succeed, and the plain text instruction can be executed. So we are relying on CompCert. So we know that it's a certified C compiler, formalized and verified in CoC, with so the limitation of compiling up to assembly. It has different backends, including RISC-V. The assembly state is basically given by memory and registers. The memory model separates code from data, and CompCert is based on a chain of passes that corresponds to translation between intermediate languages. There is a state transition semantics associated with each language, and there's a forward simulation proof for each of the compiler pass. And in the end, we achieve a backward simulation result relying on the determinism of the assembly code. Mach is the last platform independent language before assembly, and what we achieve is what we guaranteed is a soundness result, meaning that if a program compiles, then if a program compiles without errors, then every behavior of the compile code is already a behavior of the source code. So the intrinsic backend essentially is an extension of, so we want to extend RISC-V with symbolic encryption. The problem is that CompCert goes as far as assembly, whereas encryption actually takes place on the binary code after linking. So as a solution, we resort to an abstract model of symbolic instruction level encryption and decryption. And the main workload consists, of course, in the refactoring of the simulation proof from Mach to assembly. So here we have a diagram of the general system. On the left hand side, you see the compiler. So basically, you translate C source code to the extended RISC-V backend, which is the IntrinSec backend, and each of these layers is associated by their semantics to specified behavior, and we can prove in Coq a refinement result from the source behavior to the assembly code behavior. Then further on, the compilation process produce binary code, linking format. So the linking takes place, and after linking, the encryption, and produce the encrypted executable, which can then be fed to the processor for decryption and execution. So the development overview for the intrinsic backend includes extending Mach and RISC-V with the abstract model of encryption decryption, which is essentially a bunch of axioms and definitions as a shallow model. And we need to extend the RISC-V language with additional register instructions. So basically, we instrumenting RISC-V, and we need to give a notion of program state validity that keeps into account encryption. So basically, by requiring that encryption and decryption masks coincide in order to succeed with the decryption and carry on with the execution. We also need to extend the Mach definition of stack frame to make space for return masks. And finally, we have this refactoring of the forward simulation proofs from linear to Mach, and more significantly from Mach to RISC-V, where most of the work has been actually. Okay, so here we are zooming in on the part of the development that's more interesting from the point of view of verification. So basically, we have forward simulation proofs that are made all along the chain of translations. We have an extension of the inductive data type that represents stack frame, and similarly of the data types that represent the instruction set originally given for RISC-V. Plus, we have some definitions that provide the packaging to represent encryption and decryption. So the instruction level encryption protocol basically, as we already mentioned, the cryptographic block coincides with the function code block. So we associate each function block with a stream cipher. The function entry mask is stored in the program in the code memory at the start of the block, and internal masks are sequentially determined by the stream cipher. So basically, the processor knows the next mask function. Then when the critical points when jumping to a destination, which may either be a label or a function, essentially we need to load the mask for the destination, and secondly we need to store on stack the return mask together with the return address as usually done. And when returning when a function returns, let's say, we need to load from the stack the return mask again together with the return address. So the instrumentation of RISC-V comes with the addition of 3 registers for masks. You have a mask count, we've already mentioned, which points to which contains the mask for the next instruction to be executed. We have a mask branch register, where we can load the destination mask before executing the jump. We have a mask return register that's similar to the return address register in a way. It's needed to pass the return mask, which the callee will push to the stack in the prologue and pop from the stack in the epilogue. And conceptually, at least, we have 4 additional instructions. One to load the destination mask for label function identifier, which can be statically computed and so is protected by encryption. We have another load instruction to load from code memory the destination mask pointed by register, which becomes known only at runtime. And we have store of the return mask on stack and load of the return mask from stack. And here we get an example of the assembly code that is produced by the compiler. You may notice the ECR instructions are the crypto ones, and you basically you turn a simple C code into this sequence where you have 2 labels for the branching and the return, and you have store SW is for storing a mask to the stack from the return mask register and so on. So we are going to look now at the verification. So we have a condition that express the success of decryption, and basically says that the mask containing V2 is generated from the point contained in V1. So basically agrees. So the decryption mask agrees with the implicit encryption mask, and we have a valid step relation which extends the RISC-V step relation. This basically consists in saying that given the PC that points to a certain instruction, and given the meaning of that instruction in terms of transition step, which is given by TS, that's actually the transition step from the original state to a new state. And here we need to add an additional condition, which is the valid mask at PC condition. And it's a DS line. So from these definitions, we also need to add a revision of the match state notion, and then we can actually get a new forward simulation theorem, which basically states that starting from a match state, which is matched by a valid assembly state, we can always produce a valid assembly state that matches the target state in the Mach transition, and the two states are going to be associated by a valid assembly transition, which can be made of more steps, but the second disjoint guarantees that there will be no stuttering. And of course, by determinism of the target language, this forward simulation can be turned into a backward one, which gives a soundest result. So from the point of view of the security aspects, we can think in terms of control flow graph, and with respect to the forward edges, the only access to the function is from the start, because we need an entry mask, and of course we can assume, at least symbolically, the next mask, the next mask function is private. Direct jumps are protected by encryption because the address can be computed statically, and therefore is encrypted with the code, with the rest of the binary code. In the case of indirect jumps, well, the mask is stored with the function at a conventional location. So it is safe as long as the conventional location cannot be guessed. Whereas regarding the backward edges, the stack is not protected, so stack pointers are actually vulnerable. And in order to look further, we need to consider data encryption and fat pointers. That would be our plan, actually. We've also some work in progress. One branch involves the fact that cryptographic blocks don't need to be function blocks. So we can introduce labels to reset the stream ciphers at arbitrary points. This surprisingly makes the encryption model considerably more complex, because the encryption function comes to depend on the code, not only on position. And it helps shift into a different syntactic notion of straight line code, which plays an important role in CompCert. It's straight line code is essentially code without jumps. And the other branch of our work in progress involves introducing an additional language, an intermediate language between Mach and assembly, which we call pseudo assembly, which basically is the Mach instruction set with the semantics more similar to assembly, in the sense that the stack is a memory stack, is not an independent data structure. And breaking down the translation from Mach to assembly into 2 bits, into 2 steps, can actually help in reasoning about security properties, because it highlights the impact of the shift in the instruction set. So I conclude saying we have a certified compiler which supports instruction level encryption. It's lightweight encryption, so the overhead is comparatively low. It's taken about 7 months person, approximately 6,000 line code added. And the main hurdle has been some loss of reuser with respect to standard CompCert due to change of in some notions, notably straight line code. And further work, we would also like to improve modularity and look at the memory model, introducing fat pointers and going up and proving formally security properties. That's it for now. Thank you. So sorry, I can't hear you.
No question in the room.
Oh, okay.
Marco, you have one in the Q&A. Yeah.
Okay. So basically, the security properties that we would like to consider are about the fact that under the assumption that the next mask function cannot be guessed, then the only entry point for a function is the start of a function, and under the assumption that the location where the conventional location where the mask is stored, then the forward edges, the direct jumps at least, are safe. So this concerns the existing compiler. And challenges, well, I mean, the biggest thing we've seen from this development is actually that adding, so building a model around a layer in CompCert can be effective, but it can depend really a lot on the kind of model that you want to build. And from this point of view, it's probably worthwhile to look at how it's possible to make a compiling chain like that, CompCert, particularly modular and supportive of reasoning that is essentially reasoning about properties of the programs, that it goes beyond the simple processing of the language. So the definition of the translation and the proof concerning the translation. Yes, there's a link in the abstract. So there's a repository where you can find the compiler and the work in progress on two separate branches.
Marco, I think we're not hearing you. Say something. Nope. Okay, well, we're not hearing you in the room. Can folks hear Marco online?
Yeah, I can't.
Okay, well, let's thank the speaker again.